Hey everybody out there, we'll get started here in a couple minutes. Thanks for coming to a little late night review session here about calculus. So how's it going? Hopefully you're all doing well, staying healthy and not getting too stir crazy. We're doing okay. Obviously we as a teacher, it's been a full day of school, and then so planning. So this is going to be a nice way to end. It'll be nice. I like calculus. Hopefully you all like calculus at least a little bit too. Maybe you'll like it more at the end of this. All right, we'll just wait another wait another few seconds here, see if we can get a few more people. Yeah, Pearl, I like it. I like the enthusiasm. Good. Good. You come to the right place. Looks like you guys know each other. Well, how you doing? Nice. Very good. All right, so it's 9:01. So I want to reward you for being on time. So my name is Bob Amar. I'm a high school teacher in the Atlanta, Georgia metro area, and I'm really happy to be here tonight talking with you about separable differential equations. That's one of the last topics that's still on the AB exam. It's Unit 7 if you're following the AP guidelines. Segev, this is going to take, I've got about an hour here. I don't think I have an hour's worth of material necessarily. I can make it last for an hour. If any of my students are here, you know that I can make anything last for an hour. But as far as questions that you might have, I want this to be super useful for you guys. And so if you have questions, just pop them in the ask a question spot. And don't, as long as I present what the technique is, I'm really not that worried about anything in particular. I want this to be a useful thing for you all. Right. So real quick, let's just to show you what we've got going on here. Some of you may know Fiveable for things like AP World and and other AP US, AP Euro, but we got calculus stuff too. And so this is a Math Mondays basically. And so this is the closing event for Math Mondays. You can definitely come to any of these for free. Also look into our cram passes that we've got going right now. If you are interested in more of this, next week, Ms. Megan Dreyer will be talking about the existence theorem. So, all those things that end in T. So your EVT, your IVT, your MVT, all that stuff is going to come up next week at this time. So I want to invite you back for that as well. And I know that those are a lot of different theorems that show up all the time. And with the new format that the AP exam is taking, justification will be even more important. So all of these techniques are really good to review. So we're aiming to provide you something useful here. This is, I think, the first stream or guide we have on Unit 7 which involves differential equations. So we really wanted to get something on the books here. AP Live is doing the first part of this right now. They're doing slope fields and just the general theory. So we're beating them to the punch a little bit. We're hopefully you find this useful and you come back for more. We'll be reviewing throughout the month of April and May, whenever the AP exams turn out to be. Make sure you follow us at Think Fiveable on all the major socials. Subscribe, like, all those words that streamers use and stuff like that. So let's go ahead and let's get this party started here. I'm mainly going to concentrate on just the technique of separable differential equations. I'm going to give you a few examples that I've pulled. I'm going to show you how this appears on the AP free response. If there's time, I'm going to extend this over. Like if we're feeling really good and we have more time to chat, then we're going to talk a little bit about exponential models as well. So let's go ahead and take a moment. Let me just get you warmed up here. Now, I am not 100% sure whether you're here because you don't remember at all what separable differential equations are, and you really need a refresher, or you're super excited about separable differential equations and you want to talk about them in more depth. I'm okay going either way, but I thought I would open up with this little warm up here. So whichever one of these problems you find the most appropriate challenge for you, go ahead and pick that problem, and then just think about what the equation of the solution would be that passes through the point 0, 2. If you're really looking for a challenge, and you don't have to be looking for a challenge, then I've got an even more challenging problem. So put it in the chat if you want to see it. Otherwise, I'll leave it with these two. Okay. If you haven't learned this material yet, so someone's put in the chat, they haven't learned this material yet. Think about which one of these, if either of these is something that makes sense. If neither of these makes sense to you, look at the equation on the left and just ask yourself, write down in English what that equation means. Okay, so I'm going to give you about a minute or so, which may not be enough time for you to take the problem all the way to completion, but I want to aim for kind of the middle here. It's okay if you keep working through. And again, if you have a question at any time, go ahead and put that question in the Ask a Question section. If you want to offer an answer to one of them, I will ask you to wait a few seconds, and then I'll tell you can put some answers in the chat. In the meantime, you can watch me turn my head a few degrees. And then back. I'm serious. I'm very stiff from having sat down at a chair a lot today. Okay, it's fine if you blank. We are going to go through these two problems. I'm going to talk about what the solutions look like and what the process looks like. So hopefully some of this stuff will look familiar from your class. All right. If you've got an answer to either of these and you want to throw it in the chat, feel free to do so. And in 30 more seconds, I am going to take us through a solution. Okay. Got some answers coming in. I'm going to say which one it is. I should have labeled these like A and B. So we'll call the one on the left A. We'll call the one on the right B. My chair is very squeaky. Sorry about that. Okay. Hopefully everybody can now see. I need to focus this. Hopefully everybody can now see my screen, my whiteboard screen. There we go. All right. By the way, if you happen to want a challenge, there's an equation down there at the bottom if you would really like to give that a go. Okay, so if we're ready, I have no idea what just happened there. All right. I love technical fun. All right, let's go ahead and see if we can just erase that. Nope. Okay. All right. Well, it's fine. You can all see the equations. Okay. So this, when looking at this first equation, you see on the left, it says dy dx equals x. This is what we call a differential equation. The solution to a differential equation. There are actually two types of solutions, but let's just stick with this for now. Some function y of x that satisfies these particular properties. Okay, so let's look at the one on the left first. This is a function dy dx where dy dx equals x. So in other words, the derivative of y with respect to x is itself x. And so typically what we do in this case is we integrate both sides with respect to x to recover the y. But this is not the only function whose derivative is x. So you might, if you've done an integration unit, then you know that there's a plus c that gets added on to the end of this. This is called the constant of integration. And since you know that it goes through 0, 2, we can use that fact to solve for c. So if y is 2 and x is 0, then c must be 2. So this gives us a final answer for the first equation of y equals 1/2 x squared plus 2, which I see a lot of you in the chat nailing that. So that's perfect. That's excellent. Okay. So that is the problem on the left. Now you probably noticed that the problem on the right is a little bit different, because that on the right isn't x. That on the right is y. So if I try to integrate that with respect to x, that's not going to work because that variable's not y. You know that there's an issue with the chain rule and everything and so on and so forth. So what I'm going to do is I'm going to show you the technique that we use. This technique is called separation of variables. I'm not going to prove it super rigorously. I do have a slide that talks about it, and I can talk you through it if you want. But let me just show you what we do. Basically, what we do is we separate, and this is reason we call it separable equations. We separate the y's and the x's. Okay, so I'm going to move the y by division. I'm going to divide both sides by y, and that's going to give me 1/y on the left-hand side. And then at the same time, let me get rid of this line. It's annoying me. Then I'm going to multiply both sides by dx, basically. Okay, and it looks like we're playing hard and like really weird things with math. Okay, it looks really weird. Doesn't look like that's the way math should behave. But it turns out that this is a fine process to do for solving equations of this sort. Okay, so the reason it's 1/y is that we're dividing both sides by y. It's dy dx equals y. Right? And so to move y from the right-hand side of the equation to the left-hand side, I have to divide by y. And so this gives me, that's why there's a 1/y. And then I also multiplied both sides by dx. So the dx is, and I'm going to put in heavy quotation marks, cancel, right? So these dx's would cancel, these y's would cancel, and that leaves me 1/y times dy equals dx. And then I'm going to do something weird. I'm going to integrate. And I'm going to integrate both sides with respect to the variables that I have on those sides. And it looks like I shouldn't do that, but it actually works. Okay, so let's ask ourselves, what function has a derivative of 1/y? And if we go think back to what we've done in class, hopefully you can pull up that function is ln of the absolute value of, yes, it's ln. And because it's y, first off, on this side, it's ln of the absolute value of y, and not x, because the variable is y. The integral of dx, if you think about it, there's a hidden 1 just kind of hiding out in there. You can't see it, but it's there. And therefore, that leaves just x plus c. Okay. Now, you wanted to know what the solution was through the point 0, 2. Okay, I can solve it here. This is actually fine to do. We got ln of 2 equals 0 plus c. So that just leaves c equals ln 2. So ln of the absolute value of y equals x plus 2. Okay. But this is not a function. Right? This accepts both positive and negative y's. So to simplify it, I need to isolate the y. And I'm not, my slides are slightly misbehaving here, so let me go ahead and clear that. Okay. So I'm now going to raise e to both sides. And e to the ln, that just leaves the absolute value of y. And that leaves e to the x plus 2. Now you should remember from your studies that the absolute value of y then leads to a plus or minus. But because I know that the point is 0, 2, sorry, this is an ln2. Because I know that the point is 0, 2, I know it can't be minus. And so that leaves me y equals e to the x plus ln2. And if I wanted to, I could use the laws of exponents to split this up even further. And so recall that if the exponents are added on the inside, then it's just the same base multiplied over. And so that tells me y equals 2e to the x. Sorry about the ln2 there. Okay. I will reveal the answer to this challenge problem in a moment for those of you who've tried it. But I just want to see if you have any questions about these two questions. Okay, Hunter. Hunter, you are so close. Hunter, you're so close. I want to ask you if that point goes through that equation that you gave me. Okay, where am I getting x plus ln2? I have to come all the way back up to here. Okay, so right back over here where I solved 1 over y dy equals dx, and then I integrated, then I got x plus c. Okay, and then I used the fact that the point was 0. The point that it passes through is 0, 2. I know that the equation has to that I end up with has to satisfy the condition that it passes through 0, 2. So I can substitute 0 in for x and 2 in for y, and then solve for c. So hopefully that makes sense. Maria is also so close. Also so close. Also so close. Okay, I'm going to reveal the challenge problem, and then if there's time, we'll come back to it. I like writing in this. So here is the solution to the challenge problem. Yeah, the -1 there doesn't turn out to be a -1. The solution path generates a plus or minus. Okay. All right. So hang on to that. I'm hoping we have time to come back to that because I really like that question. But all right. So we have just now talked about the reason why we might care about these equations. I want to just go back and look at the example one more time, because I think it's important to be able to think about this example conceptually as well. All right. So when we have these examples here, the equation on the right is basically saying I would like a function y that is its own derivative. So if dy dx equals y, think about all the functions you know that when you differentiate them, they are their own derivatives. The first one that comes to mind, and kind of the only one that comes to mind really, is e to the x, right? So if you've taken the derivative of e to the x, you know that it's its own function. And if you then also think about the function that we got, y equals 2e to the x, if you take its derivative, the 2 is just a constant. And so y equals 2e to the x will also be its own derivative. That will become important later on. So let's talk about what the separable differential equation scheme really is, what it looks like, and how we can use it. Okay. When we have a differential equation that is separable, what's true about it is that we can get all the y's on one side and all the x's on the other. Okay. So I claim that the function that we're looking at right now, or the differential equation that we're looking right now, is separable. You might have seen this in your textbook. This is what we call a separable form. So in this case, the f of x would be x squared, and the g of y would be y squared plus 1. And so what's basically happening is you have a bunch of x's times a bunch of y's, right? And you can separate them out in that way. And if you can algebraically do it, then you can solve the equation simply by dividing. So if I divide all the y's onto the left-hand side and I multiply both sides by dx, I can take the integral on both sides, and that will give me the answer. Okay? And this is the general path. I think if I show you a few more, it will probably fall into place. Now, these are going to be examples of varying difficulty. So hopefully that will give you something to chew on, no matter how you're coming into this. So these first two examples are always I like to start with. I like to start with dy dx equals y, because not only is it a very simple and overall, yeah, exactly. Except we're going to just go from a simpler y to a more complicated g of y. And then we'll see how many rules we can come up with and all kinds of different things to solve all these problems. Okay. So I think that's a good introduction. So these are the three examples that we're going to work. Okay. All of them have a little bit of a trick to them. And we're going to also differentiate, no pun intended, between what we call general solutions, which are just which are really just the family of solutions that are given by the plus c form, and then what we call particular solutions, like we did in the warm-up, where we actually solved for the c by figuring out by substituting in the point that it passes through, and I'll show you some different ways that these are written as well. Okay, so this is where we're headed next. Okay, so back to the whiteboard. Let's get the size right. Here we go. Okay, so here's the first example that we're going to do, or the first set of examples that we're going to do. I'm actually just going to make a lot of room down here, and we'll work them all individually. All right, so let's start with just this first one. So dy dx equals x squared y squared plus x squared. Okay. Now remember, the goal is dy dx equals a bunch of x's times a bunch of y's. Okay. And I need to be able to separate all the y's out into one group or one factor. I need to be able to separate all the x's out into one group or factor. In each case, it's generally okay if a number sticks around with it. All right, so I would love ideas as to how I could rewrite this equation in separable form. How can I get something, how can I just get an expression with x's times an expression with a bunch of y's? Okay, good, this is good. So everyone is saying factor out the x squared, and that will leave me with x squared times y squared plus 1. How's that? You feel good about that? Okay. Now I'm going to do the separation thing. So what I'd like to do is divide both sides by y squared plus 1 and multiply both sides by dx. Again, this is really, honestly, a bookkeeping technique. dy and dx happen to behave in this way. And it works mathematically. Okay. So we get a cancellation here, get a cancellation here, and that leaves me with 1 over y squared plus 1 dy equals x squared dx. Okay. Now I integrate both sides with respect to their variables. The right side's relatively straightforward. And by the way, pro tip, the minute that you take an integral, the plus c has to appear. Does anyone recognize the left-hand side? Nice, nice. Okay, so I see a couple of people who recognize that left-hand side. Yeah, yeah. You may not have run into this yet. So if you haven't done the inverse trig derivatives or yet, then you haven't seen this. Then you haven't seen this yet. That is something you should still be working on for the AP exam. Hopefully, your teacher, if your teacher hasn't taught it to you yet, and you're still having class in this day and age, you're going to be able to still learn that. Okay. So this is arctan of y. Now, because this is a general solution, that means that this is an expression that doesn't have a dy dx in it that could be solved for y if I had to. I will say that a general solution in general, because we don't know any more about it, we can stop without isolating y. So it's okay for a general solution not to isolate y. Okay. If I knew what point was the solution y passed through, then I could actually solve this for C and then get what we call a particular solution. Okay. All right. So let's grab the next example. And I think at this point, I would really love to see you try it. Okay, so that was example 1. Right. I want to see you try to get the general solution. I'll walk you through the particular solution. Annika, you can. That would give you y equals, it would be okay to write this as well. It would be okay to write y equals tan of 1/3 x cubed plus c. Okay, this is also fine, but notice where the plus c is. The plus c is inside the parentheses because the plus c appeared when we took the integrals. If you add the plus c later, you run the risk of getting the problem wrong. So just be aware of that. Okay. I think it's easier to put the plus c where you see it there. Okay, so here's that second example. dy dx equals negative x over y. See if you can get all the y's on one side and all the x's on the other side, and then when you get the general solution, pop it in the chat. Okay. All right. Okay. Seeing some answers come up. See what you all think about these answers that are coming into the chat. See if they agree with what you've gotten. If you get stuck, you can always ask a question. I see that save there with the plus C. That's one of the hallmarks of a general solution is that it has a C in general somewhere in it. Okay. In about 30 seconds, I'm going to start solving the problem. Okay, for those of you who are, again, like looking at the different answers in the chat, ask yourself where these all came from. Okay, good, Annika. So you've got the y on the left side correctly. Now get the dx on the right side. Great, Maria. Really nice. So Lily, good job. Nikita, great job. And you notice that Lily, Nikita, and Maria's answers all look slightly different, but they all work. For sure. And Hunter, you may have actually found an answer. You may have found a particular solution as well. We'll talk through it. Let's see if we all agree on what's going on. Remember that there's a that Nikita has written y squared. Annika, did that help? If I multiply both sides by dx, then that gives me two things to integrate. All right. If you're getting a little stalled out here, don't worry. I'm going to show you what it looks like. All right. So let's basically uncross multiply this one. This is kind of a neat one because if I multiply both sides by y, it's the same as dividing by 1 over y, right? And so if we are separating this out, technically I'm going to do this in just temporary colors here. Temporarily, this is negative x times 1 over y, and then probably then we can do multiply both sides by y to clear that fraction, or you can divide by 1 over y, whichever way you want to do it. And then we need to get the dx going here, right? So I've realized I've written a lot of weird work here. So let me go ahead and let me just show you where all these things are coming from. So the part in orange is where I'm clearing out the y's from the right-hand side, and the part in green is where I'm moving the dx over. Okay. And if I do all of the cancellations that these imply, then I get y dy equals negative x dx. And thankfully, this is pretty good. If we could have gotten some worse functions here to integrate. This is 1/2 y squared equals 1/2 x squared, and then I'm going to put that plus c on before I forget. Okay, this is our general solution. Now, I want to point out something that's kind of interesting. If I multiply this equation through by 2 on both sides, then technically I get y squared equals, it would not be, Perla wouldn't be wrong. Technically, when we're doing the integral, we always want to write the differential, the dx at the end, so we know that what's in front of the dx is the integrand. Like, for example, if I wrote this, I wouldn't be sure that the x squared is what I really wanted to deal with, right? And so to avoid a lack of clarity, then I want to make sure I write this so that I know that what I'm integrating is the x squared. And also, if you write dx times negative x, you might forget that what you're doing is multiplying and not subtracting. All right. As I clear through here, I get negative x squared. Now, c is a constant. I could write 2c here, but c is already just whatever number I want it to be. So in calculus, it's okay if we just say that this 2 is absorbed into the C because we didn't set a value for it. This, you can't always do it that way. And I like to at least point out that that you should make sure you think about, is it okay? Has this value of C been used in some other function yet? Here it hasn't, so there's no worry about it. But if that C was inside, like for example here, if this C was inside the tangent and then I multiplied through by 2, the 2 can't get to that plus C. Okay. All right, so this is a general solution. And that's always the first step. But then I want to substitute in the point. I'm not sure why I keep picking 0, 2. I just really like 0, 2. Third example doesn't have 0, 2. So now I want to substitute in. Let me just see what I'm doing here. Substitute x equals 0 and y equals 2. And this gives me 2 squared is 4, right? Because that's the y coordinate. 0 squared is still 0. So C is 4. And now I have y squared equals negative x squared plus 4. And the question is, am I done? And in this case, for a particular solution, it has to be a function. And if it asks for the solution, the passing through a point, it is a particular solution. The AP exam in general is very good about writing that it wants a particular solution, but your textbook may not be as good. But just be aware that anytime you're using a particular solution, it has to be a function. Okay, so the particular solution must be a function. So I'm going to use that old algebra rule where I take the square root of both sides. And then I get y equals plus or minus, and I'm going to rearrange the inside, 4 minus x squared. And the question is, which one of these do I want? Because it's still not a function if I have a plus or minus. So I'm going to look at my point, and I'm going to recognize that I only have a positive value for y. I can't generate a positive value if I use the negative. And so this gives me y equals, let me give myself a little more room. So this gives me y equals positive 4 minus x squared for my particular solution. And again, we reject the negative since we're passing through 0, 2. We can't also pass through 0, negative 2, because then it would violate the vertical line test. Right? You can't have a solution that passes through both 0, 2 and 0, negative 2. Right? This can't happen. And in fact, if you graph this equation, y squared equals negative x squared plus 4, you might remember from pre-cal that what you end up with is a circle. And technically, the part of the circle that we've ended up with is the part that only corresponds to the top half. Now, I'm going to do something that looks a little weird. Technically, the part that we've graphed has open circles on the end. And I want to know why. Because this function, y equals square root of 4 minus x squared, it's defined technically at x equals 2 and negative 2. And so if you have ideas about why I'm actually going to reject those endpoints, in other words, the domain of this solution is negative 2 to 2, not including the endpoints. You have ideas, I'd love to know. I'd love to hear from the chat. This is kind of like Jedi level stuff. And I'll give you a hint about this. Look at the original equation. Okay. All right. All right. Good. Yes. You're all right. You're all right. That is wonderful. You've probably all heard that. Has your teacher ever done 0 on the top? Okay. 0 on the bottom. No way. Your teacher ever done that? Just a question. Because that's what's happening here. So yeah. And that's the reason why you can't include the endpoints in this case. So that's one of my favorite things there too. Okay, I really like this last one. And we are here just to solve separable differential equations. And I think it's good practice. So let's definitely take a look at this last one. And if you look at the original thing that I wrote, I said that the particular solution passes through 1 comma pi. Another way you'll see this written is either y. I think this is the most common way that you'll see it. Y of 1 equals pi. So this is what we call the initial value or the initial condition. Okay, so I would love it. I'd love to give you a chance to solve this on your own, all the way through. Yes, and so I've been giving. I hope I haven't given you the wrong impression that we can set the initial condition anywhere we like. The initial condition is most often 0. For exponential functions, we often like to set it at 0 because it has a nice meaning. But it doesn't have to be 0. We can set the initial condition anywhere we like for a differential equation. Okay. The initial value, it might be a term you've heard in your math class that involved an exponential function. And that we do generally call the initial value. And that's usually when x equals 0 or t equals 0. So those two things are slightly different, but that's a good point. All right. I want to give you a little bit of a head start here. If you've got a question, if you get stuck anywhere, please ask a question. Give you about 45 more seconds of head start. This one's all about the trig. Okay. All right, I'm going to go ahead and start working through this problem. It's got quite a few moving parts. So let's take a look. It's the square of cosine, but you notice that it's on the right, Nikita, it's on the right side. So I did you a favor here and I put it in separable form for you. If you will permit me to, when I divide by cosine squared, y, okay. Okay, so 2x equals dy dx times 1 over cosine squared. And watch out, that's a y, a cosine squared y. Okay. I would like to write this in a form that you may recognize a little better, because we've canceled out the dx's, they leave a 1, and so I've got a 1 over cosine squared, which is secant squared. Oh, I see something I really like in the chat. See it. I see it. See it. Okay. All right. And so is everyone comfortable with 1 over cosine squared is secant squared? Because I want to see if you recognize that function on the left-hand side. Pearl's giving you a little bit of a hint. This is really, it's really good work. I like this one a lot too. It's very intricate. Okay. Okay. So think of a function whose derivative is secant squared. That function, as far as I can remember, that function is tangent. So on the left side, I have tan y. On the right side, I have x squared plus c. Okay. So the big reveal. Let's see if I agree. Okay. So to do this, you also need to get the tangent of pi, right? And so let's see if we remember our unit circle, right? So the tangent of pi, that's equal to the sine of pi divided by the cosine of pi. The cosine of pi is -1, but the sine of pi is 0. Okay. Yeah, those trig functions will get you, and they do expect some knowledge of that. I do find that, with the new AP, with the new AP exam, I don't for this year, I don't know how heavily you're going to need to have the unit circle memorized. But if you're having to look up the unit circle values all the time, it may slow you down. Okay, and so here I recognize that the tangent of pi is 0, and this gives me c equals -1. Therefore, tan y equals x squared minus 1. Therefore, y is arctan. I'm going to write it as tan inverse because you'll also see that as well. So wonderful job, all of y'all. Yeah, absolutely. Yeah, absolutely. Like if you can use them efficiently, you can have some. I would recommend you have some reference material and not burden yourself with having to remember these in the moment when you need it. Yes, and I would say absolutely it's open notes. But if you're still taking assessments with your teacher, you may want to memorize them to the degree your teacher expects it. Yeah, I'm seeing a lot of really good work. I hope this is helping. Again, feel free to pop a question in the ask a question section. Then you can also go back and look at the videos later. But yeah, really good work. Okay. Let's see. I don't think I have to really go back to the other presentation. Okay. I pulled a couple of I pulled this problem in particular. I pulled this problem in particular because it's a nice synthesis of all these different ideas. If you've gone to the Fiveable page and you've pulled down the slides, you can print this out and do it yourself. In the interest of time, I really do want to just focus in on the initial condition piece. Okay, but I am going to talk through part A. And there's a specific reason I want to talk through part A, and that is because it has an important implication for the answer to part C, or at least I think it helps you see the answer to part C. Okay. Put a thumbs up in the chat if you've seen a slope field. If you feel like admitting to it, that's fine. Or if not, I'm not gonna force you to embarrass yourself. Or put a thumbs down in the chat if you haven't seen a slope field before. While you're doing that, I'm gonna make a t-chart. I guess it's more than a t-chart. Good. Okay, that's good. So I see 6 different points at which I have to evaluate slopes. And I remember from dealing with slope fields that what I'm really doing when I plot a little segment of slope is I'm revealing what a solution very close to that, what a tangent line, to that solution would be. I'm basically plotting little pieces of the solution if they were there. Okay, if the solution was passing through that. So that's what these little segments are for. They help you figure out the direction that a solution that did pass through that point would go. So it all depends on what the initial condition is. So I'm going to quickly go through. When y is 0, I notice that as long as when y is 0, as long as the denominator is not 0, and that's why I left off all the x equals 1 points. When y is 0, those slopes are going to be 0. Okay, and then for this point, 0, 1, I get 1 over negative 1. And then for 0, 2, I get 2 over negative 1. And then the opposite happens. The opposite thing happens for when x is 2. I get 1 over, for y squared over x minus 1. When y is 1 and x is 2, I get 1 over positive 1. And then I get something interesting, don't I? Wait. Okay. I forgot to square the y. That's sad. Okay. There. Those look more like the right numbers. Okay. Right. So then I plot, when I plot a slope field, all I need to do is just make sure that the differences are clear and that slopes that are steeper are clearly steeper. What happens to this differential equation at x equals 1? Well, you can't divide like this when x is 1, the dy dx doesn't exist. It's undefined. Okay. I'm not going to draw an asymptote or anything there. That turns out to be what the functions will look like in general, except the one approaching from the origin. 0 over 0 is different than 2 over 0. That's a story for another stream. But you are going to see vertical asymptotes for all of these different equations that are either to the left of x equals 1 or to the right of x equals 1. Okay, so I like this one a lot because it has a slightly different feel, right? So let's make sure we can solve this differential equation. All right, so dy dx equals y squared over x minus 1. Okay. Take a moment and separate that. I'm just going to go ahead and make sure I give you the answer. I don't want to run out of time here, so I'm going to make sure I just give you the answer to this one. See if you agree with my separation and then my general solution. Okay, I've got a question. All right, I got a question about DNE and undefined. Here's the way I think about it. Functions are undefined and limits don't exist. And that's the way that I think those questions should be answered. My belief from seeing a lot of people talk about this, like hearing a lot of readers talk about it, is that that they generally let it go. Like if you say DNE when you mean undefined and vice versa, they're okay with it either. They're okay with it either way. But to me, limits don't exist. Functions aren't defined. And so that's my general rule of thumb. So that's why I say dy dx is undefined in this case. You are welcome. All right, let's keep them separated. Hey, okay, so let's do 1 over y squared dy equals 1 over x minus 1 dx. Okay, that went by in kind of a hurry, so let me fill in how I got all these different pieces. Okay, I'm doing that to clear out the y's on the right-hand side. Then 1 over y squared dy equals 1 over x minus 1 dx. What I like about this problem is that the way that you anti-differentiate the left side, you take the integral of the left side, is different than the way that you integrate the right side. So you have to recognize that on the left side, what you have, just because you have a 1 over something doesn't make it an ln. This is y to the minus 2, right? And so its integral is negative 1 over y. And so you can double check that by differentiating this. It's y to, in other words, this is negative y to the minus 1. Take the derivative of that by using the power rule and see that you get the answer there. But on the right-hand side, it is an ln. Now, the minus 1 is a little bit of a problem for our general rule because we expect to see 1 over x. In general, when you're shifting a function to the left or right, it doesn't really affect anything. This is what you end up with. You just end up with ln of the denominator as long as it's a shift over to left or right, and the x doesn't have a coefficient attached to it. If it was 1 over 4x minus 1, then we'd have to deal with the 4. It would end up being 1/4 ln of root x minus 1 thanks to the chain rule. But just convince yourself that we're okay with this. And so when we substitute the initial conditions, we get f of 2. Now, here's another way that you see it, right? Where they use f as the name for the solution. Okay, so that's just another way that you'll see the initial condition. Those AP writers is tricksy, right? And so we got x is 2 and y is 3, and so this is negative 1/3 equals ln of 2 minus 1, which is the ln of 1 plus c. But hey, ln of 1, everyone's favorite, every math teacher's favorite, unrecognized, simple answer. Well, 1 over x minus 1 does become x minus 1 to the raised to the negative 1 power. It does, but then we have to take its antiderivative. And there's no way to use the power rule to generate a power of negative 1. Right? So try to think of a function that when you differentiate it, and like think of an x to what exponent, right? Would it have to be x to the 0? Would x to the 0 turn into x to the minus 1? That doesn't really work because x to the 0 is actually 1 in general. It's a constant, unless x is 0. But that's a story for another stream, right? And so x to the first raised to the negative 1 is what this part really is, but it doesn't actually. We have to use ln to find its antiderivative. And so in this case, c is negative 1/3. And so we have to now ask ourselves what our solution should be, right? And so we have negative 1/3. This is a good way to end. We have negative 1 over y equals ln of x minus 1 minus 1/3. And the thing that we need to ask here is there a special thing that we need to do to isolate this as a function? It turns out in this case that we really don't have to, thankfully, because what we can do is we can just take the reciprocal of both sides. And we're going to get, and let's take the negative reciprocal of both sides so that negative cancels. Okay. And so that tells us what the form of the final answer on the right-hand side looks like. It's kind of a weird one. That is a weird looking function. All right. All right. Let's see if we have any last minute comments, questions, or concerns here. Doesn't look like it. So that's a typical presentation of on an AP question of separable differential equations. I'm gonna, let me just skip to the end here. I wish I had time to talk about this, but I do want to show you that that often equations that appear on the AP exam that they can be solved using separation of variables. And when the right-hand side is a linear function of the dependent variable, like for example, if you replaced b with y in the equation you see here, you would see dy dt, but here it's just capital B. Equations like this, where the dependent variable is in a linear term on the right-hand side, those will always turn into exponential models. Their answers will always be in terms of e. So I think it's a really, I think it's a really cool thing that happens with equations like this, and all of them are solved using separation of variables. Sure. I think I'll just run over a couple seconds here. All of these equations that look like this, they all become exponential models, because what happens is you end up with ln of this part. You always end up with ln of that part on the left-hand side, and then to resolve the equation, you always have to raise e to both sides of the. And so what that's going to do is create an exponential model on the right-hand side. And so. And so these always turn into exponential models. But now that you've seen separation of variables, that is how all of them are solved. Does that make sense, Pearl? Yes, absolutely. And that's you know, you saw on the slides that that's what happens with any exponential model. Let me go back to that real quick, because I have to give you the sign off anyway. So let me show you where that is on the slides, in case you want to refer to it later. You're welcome to refer to those slides later. For sure, I hope they're helpful. Right. So come on, screen. There we go. All right. Yeah, that's where the CE to the KT comes into play. And so any model that looks like this has an initial value as that C constant where you have it. And that's this initial value thing, I think, what you're talking about earlier. All right. Well, I've had a wonderful time. Hopefully this has helped you with the concept of separation of variables and what we call separable differential equations. They're a very common technique for solving equations at this stage of the game, and they're the basis for the beginning of the study of differential equations at the college level. So it's an important topic. I am extremely happy to have had the opportunity to work with you and talk with you. I again want to invite you back next week for a presentation on existence theorems. Again, that's that EVT, IVT, MVT stuff. Oh, sorry, you missed it. We were talking about separable differential equations. The slides are posted, and you can watch the replay. So I worked through a few different examples and how to separate the x's and the y's on each side. Okay. That's it. I think I have to let you go now. But you know, do come back for more. We're here to help you as much as we can. And you know, as in this time of great uncertainty, we want to hopefully be a steady spot for you, and you know, give you. There are lots of resources that you can choose from to learn about these materials, and you know, we're all just trying to help you out as much as you can and give you some power over this thing where we don't even know what it looks like yet. April 3rd, they're going to announce a lot of stuff. So I'll be excited to hear that. I know you guys will be too. Thank you guys so much for your attention and your work. Again, hopefully you picked up something that you can use out of this, and I will talk to you all later. Thank you so much.